Hello, I'm Larry Glass, the Chief Science Officer of Neuren Pharmaceuticals. I want to start out by just thanking FAST, the good folks at FAST, for the invitation to present, for you to learn a little bit about Neuren. And I want to thank all of you who are listening or watching for your interest. So I'm going to give you some background on the company first, and then talk a little bit about the science that underlies our programs, and then give you a status update as to where we are. So Neuren is an Australian company, although we're virtual, even pre-COVID. We have two drug candidates in clinical development for 5 different neurodevelopmental disorders. The lead program, as you may know, is in phase 3 for Rett syndrome. And we're now moving with a new drug into trials for Angelman-Phelan-McDermid syndrome and Pitt-Hopkins, which will start in next year. The drug candidates that we're developing are synthetic analogs of IGF-1 metabolites that are naturally occurring in the brain. And these analogs replicate the activity of the natural molecules, but they're more bioavailable and stable, and they are more readily available across the blood-brain barrier. The broad aim is to have an effect by improving the connections and the signaling and the structure of neurons and dendrites. So this is just an update of our product pipeline, showing where various things are. You can see that Angelman down there is set to commence in 2021. It's currently in a phase 1 study. We have orphan designation in the US and EU for Rett and Fragile X, and we have orphan designation in the US for Phelan-McDermid, Angelman, and Pitt-Hopkins syndromes. And we have, as I think we've announced, we also have orphan applications pending in the EU for those 3. So a little bit behind, excuse me, behind the molecules is that little background on IGF-1 here. IGF-1 is an essential growth factor responsible for development, maintenance, and repair of synapses and cells. It's expressed early in development and peaks at around puberty. It's expressed by both neurons and glial cells. In the brain, it's rapidly metabolized to a truncated form of IGF-1 called DES, IGF-1, and GPE, which is glycine proline glutamate, which is the last 3 peptides on the molecule. GPE then goes on to be further metabolized to cyclic glycine proline, or cyclic GP, and the cartoon on this page will show you sort of how things happen. So IGF-1 is expressed, it binds to the IGF-1 receptor. Whatever is not bound to the IGF-1 receptor can be metabolized, and the brain, as I said, is rapidly metabolized to the truncated form and GPE. Both IGF-1 itself and the truncated form are very active in the PI3K, AKT-mTOR, and RAS-MAPK, ERK signaling pathways in neurons, and it's one of the major regulators of synaptogenesis as well as metabolism and protein synthesis. GPE, on the other hand, is also very biologically active, and on its own, it regulates microglia, which maintain and prune synapses as well as maintaining signaling pathways. GPE is also potently anti-inflammatory. GPE, however, even itself is not particularly stable, and it's rapidly cleaved to cyclic GP. which has some of the same functions of GPE in that it's capable of regulating microglia and regulating inflammation at the cellular level. Cyclic GP is a synthetic analog. I mean, 2591 is a synthetic analog of cyclic GP. Now, the other thing that cyclic GP does is that it regulates the binding between IGF-1 and IGF binding protein 3. And in doing that, it regulates the availability of IGF-1 to the receptor, so that it's part of that autoregulatory process that's very complex, but that defines the IGF-1 system. And it's the way in which cyclic GP seeks to provide or maintain homeostasis within the brain and other systems. So what we're doing with 2591 is targeting what they call synaptopathies. It's an awkward word, I suppose, but what it refers to is synapses, syndromes or diseases where the synapse, pathology in the synapse is an important part of the underlying pathology. Neurodevelopmental disorders result from very different mutations, as you know. But all of them feature deficits in synaptic plasticity, which could include regulating the strength of connections between neurons, or abnormal length and density of dendritic spines, or both. And it's the impaired signaling in the neurodevelopmental disorders that causes the behavioral and cognitive and motor and autonomic symptoms that vary, of course, from one to the next. 2591 corrects features that are common to synaptopathies. So I mentioned that it was anti-inflammatory. It works by suppressing the expression or regulating the expression of inflammatory cytokines. It addresses the problem of pathologically activated microglia, which are ineffective at dendritic pruning and maintaining the maturation of dendrites, synapses. Many of the neurodevelopmental disabilities have depressed expression or bioavailability of IGF-1, and 2591 obviously corrects that because of its role in maintaining bioavailability. And it also directly affects neuronal signaling. And what this does is it restores the balance, as I said before, the homeostasis between synaptic protein synthesis, maintenance, and repair. In mouse models of Angelman, Pitt-Hopkins, and Phelan-McDermott syndrome, 2591 has fully rescued the phenotype with 6 weeks of treatment. And it's available, it's able to correct both hypoconnectivity and hyperconnectivity. And across various developmental disabilities, the dendritic function can reflect either overconnectivity or underconnectivity. And because it's a homeostasis seeking molecule, it will correct both. The other thing is that the 2591 has state-dependent effects. So it has virtually no effects on wild-type cells or normal cells in affected animals. It only has an effect if there is a underlying neuropathological problem. And this is, of course, as I said, consistent with the role of cyclic GP in supporting the development and maturation of synapses and maintaining homeostasis. So these are this is a summary of the study that we did in the UBE3A knockout mouse, treated for 6 weeks. And in addition to completely eliminating audiogenic seizures, if you look at each graph there, you can see the last 2 bars are wild type with 2591 and the UBE3A knockout with 2591. They're pretty much the same in each of the various measures. And the second bar in this is the UBE3A knockout mouse. So as you can see, in anxiety and locomotion, in functional behavior, activities of daily living, sociability, physical capacity, and memory and cognition, 2591 completely restores the UBE3A knockout mouse phenotype to that of the wild type right across the board. So this is the last slide, and it covers where we are right now and where we're planning to be. As I said, we've demonstrated efficacy in the mouse models. We've confirmed recently that this molecule is 100% orally bioavailable. With oral administration at 1.5 hours, there's the equivalent concentration of the drug in blood and CSF, and at 4 hours, there are equivalent concentration in blood and brain. So, you know, there's clearly a strong oral bioavailability effect in terms of cerebral circulation. What we're doing is leveraging the extensive experience that we've had with the Rett and Fragile X programs in CMC, which is the manufacturing component, non-clinical safety, which is safety, pharmacology, and toxicology, and the clinical and regulatory processes that, you know, we learned about when bringing Rett and Fragile X through to where they are. We learned from our mistakes, and where our ability to leverage that means that 2591 is on a faster trajectory than trofinetide or 2566 was. So we've completed all of the safety, pharmacology, and toxicology studies that we need for a pediatric population study for 12 weeks, which is what our plan is. That was a major accomplishment. Not a very exciting one in some ways, but it's absolutely essential for the IND. And because we're now confident of our safety and toxicity profile, and because we're confident of the clinical benefit that emerged in the animal model from 2591, we've initiated a manufacturing campaign for phase 2. So that's a statement of our confidence in the program. The manufacturing is going well. We've made good progress there. We've initiated a phase 1 trial in healthy volunteers, which is currently underway in Australia. And we'll bring those data together with the pharmacology and toxicology and manufacturing and clinical plans to the FDA next year, and be able to take this molecule into phase 2 trials in pediatric patients next year. So thank you very much. Been good talking to you. I hope this was helpful.